Now we are going to discuss example problem of impedance matching using stubs. This is a transmission line circuit where you have a source connected to a load of 70 plus j60 ohm through a transmission line of characteristic impedance Z0 is equal to 100 ohm. Now if you look at this circuit, you can find that your load and your line are not matched because load is 70 plus j60 ohm and your characteristic impedance is 100 ohm. Now what do you mean by impedance matching? The meaning of impedance matching is you have to make your load impedance equal to your line impedance so that both of them are matched. Now that means if you look here, you can see that your load impedance is 70 plus j60 and you have to make it equal to 100. Now if you split this is a complex number, so if you split the load impedance into two, you'll see that your real part 70 should be equal to your 100 because this has no imaginary part, and the imaginary part of j60 should be equal to 0. So the first step to do that, or what we are actually doing with Smith chart, is that we will try to normalize the impedance. So we have ZL is equal to capital ZL by Z0, which is 70 plus j60 by 100, which is 0.7 plus j 0.6. Now if I normalize Z0 also, Z0 by Z0 will be equal to 1. Now as I told you before, the meaning of matching is I have to make the real part equal to the real part. I have to make my imaginary part equal to 0. So if you look at here, the whole idea is I have to make my 0.7 equal to 1 and I have to make j 0.6 equal to 0. That means the real part should be made equal to 1. The imaginary part should be made equal to 0. Both of them are normalized values, and this is what we do by using stubs. If you see here, we have ZL is 70 plus j60 ohm, Z0 is 100 ohm. We have normalized it to 0.7 plus j 0.6, and we are going to plot this normalized value of ZL onto the Smith chart. So you see here, this is 0.7 and this is your 0.6 and this point is your ZL. Okay, so this point is now your ZL. Now the next step is we will draw the VSWR circle. So we have drawn the VSWR circle and this point is our ZL. Okay, so this is your 0.7 and there you have your 0.6 and this is your VSWR circle. Now if you see here, the unity circle, that is R is equal to 1 circle, this is your unity circle. It will cut the VSWR circle at 2 points. One point is here and another point is here. Now if you remember, our aim was to make the real part of small ZL, that is normalized ZL, is equal to 1. So keeping that in mind, we have to look at the point where the R value is equal to 1. So if you see here, you have 2 points. Let me mark this point as point A and this point as point B. Now always remember that from your load you will move clockwise and you will consider the point which is nearer to your load. For example, if you see here, you have point A, here you have point B. If you start from ZL and you start moving clockwise, the first point that you will reach is point A. So we are going to consider point A here. So if you remember from what I told before, this is your ZL and this was your point A where the value of R is equal to 1. So if I write here, the value of R is equal to 1 here and this is your ZL value. Now if you look at the lambda value or the position of ZL, if you see here, it is 0.11, 0.12 and 0.14. So I will write here lambda of ZL is equal to 0.114 lambda. And if you go here, the position of R is equal to 1 point, or that point A is here. This is 0.15, 152, 154, 156. So the lambda of A is 0.156 lambda. 0. Okay, so you have ZL at 0.114, the point A where the real part becomes 1 at 0.156 lambda. Now if you see the diagram of stub matching here, you can see that this is the stub and you have two values to calculate. The first one is the distance and the second one is the length. Now distance is the place where you keep the stub. That means from your load, what is the distance at which you keep the stub, and L is the length of the stub. Now the distance of the stub is calculated as D is equal to the lambda of A minus the lambda of ZL, which is here 0.156 lambda minus 0.114 lambda, which is equal to 0.042 lambda. This is equal to distance of the stub from the load. So if you see here, you can see that this is your distance. So that means the place where you connect your stub from the load. So if I mark it on the Smith chart, this would be your distance, which is denoted as D. So we have calculated, if you see the diagram here, we have calculated the distance. That means the position or the place where you have to connect the stub from the load. Now if you see here, you can see that you have one more value to find out, which is the length of the stub. Now if you go back to your understanding, we have now made, from using the distance of the stub, we have actually made the real part is equal to the 1. Now next what we have to do is we have to make the imaginary part is equal to 0. For that, see, in this point, find out what is the imaginary part. So x is equal to, if you see here and if you go back to the imaginary value, you will find that it is 0.8. So that means at A, R is equal to 1 and X is equal to 0.8 plus. So that means you can write it as Z is equal to 1 plus J 0.8. Now if you see here, we have made our real part already equal to 1. Now our aim is to make the imaginary part equal to 0. Now if I want to make J 0.8 equal to 0, what I have to do is, to J 0.8 I have to add minus J 0.8. So the answer would be equal to 0. Okay. So now what I am going to do by Smith chart is, I am going to find out where is minus J 0.8 and I will add that here. So if you remember, this was your ZL, this was your A, where the R was equal to 1, your X was equal to plus 0.8. So as I told you, if you want to make this imaginary part equal to 0 or cancel the imaginary part, you have to go to the minus point. So if you see here, you can see here, this is your minus 0.8 point. Now if you look at this minus 0.8, draw a line from the center of the Smith chart through the minus 0.8 point. You will find that the value of lambda here is equal to 0.392 lambda, which is your minus jx point. Okay. Now the length of the stub, there can be two types of stub. One is called as short circuit stub and the second one is called as open circuit. Now if you see on a Smith chart, if you see a Smith chart, a normal Smith chart, you will see that this is a point where your R value is 0, your X value is 0. And if you see this side, this is a point where your R value is infinity, your X value is infinity. That means we have Z is equal to R plus JX, which is equal to 0. Here we have Z is equal to infinity. Now impedance is equal to 0 is called as a short circuit point, and impedance is equal to infinity is called as an open circuit point. So if you take a Smith chart, this point is your short circuit, this point is your open circuit. Now if you see, you can see, understand that the lambda value of a short circuit is 0 lambda, and the lambda value of an open circuit is 0.25 lambda. If we go back to our circuit, so the length of a short circuit stub is calculated as length of a short circuit stub is calculated as L is equal to the lambda of minus JX point minus the lambda of short circuit. For example, here it is 0.392 lambda minus, as we know, the lambda of short circuit is 0 lambda. So the answer is 0.392 lambda. Similarly, the lambda of an open circuit stub is equal to the lambda of minus Jx minus the lambda of open circuit, which is equal to 0.392 lambda minus, as we told before, the lambda of a open circuit is equal to 0.25 lambda, which is equal to 0.142 lambda. So if the question is asking you to find out the length of a short circuit stub, you will do the minus Jx points lambda minus the short circuit's lambda, which is here, for example, 0.392 minus 0, which is 0.392. So if you see here, for a short circuit stub, most of the time you get the same value because every time it is 0. Now if it is an open stub, you will do 0.392 minus 0.25 lambda, which is equal to 0.142 lambda. So now we see that we have found out for this stub the distance is equal to 0.142 lambda, and the length of a short circuit stub is equal to 0.392 lambda. The length of an open circuit stub is equal to 0.142 lambda. I think this was 0.042 lambda. Okay, so these are the values that we have got for the stub. So that means if you redraw the circuit again, it will look like this. This is your ZL. This is your ZL. This is your Z0, and you are going to keep a stub here. Stub here like this, where this is your D and this is your L. Now this portion can be an open circuit or a short circuit. So this is how we do impedance matching using stubs.